Hello and welcome to Basics of Cryptography. In this session, we'll learn how cryptographic systems are built, how modern cryptographic systems work. What is a cipher? A cipher is a term used for any encrypted text message. So any plain message, when encrypted through some algorithm, becomes a ciphertext. And a very simple example is like hello. If you shift every character by 3, it becomes KHHOR. And this is a ciphertext because it does not have the original meaning and you have done some algorithm to make it a ciphertext. The same message when sent to other party just shifts back 3 characters back and makes it hello back. The plain text can be retrieved. So in this case you notice 2 things, the key and the algorithm. The key is 3 and algo is to shift characters alphabetically with the key amount. So this is a very simple cryptographic system used by Julius Caesar in those days. And one thing to notice here is that the algo and the key is known to both parties. The same key is used for both the parties. Okay. Now we'll see what are the cryptographic terms. Now hashing is very important in cryptographic systems. Hashing basically means you take any length of the message and it converts to a fixed length output. There are various techniques of hashing like MD5, SHA1, then SHA2 series is there. SHA256 is one of the example, where the output is 256 bits. MD5 gives the output of 128. So idea is that you cannot retrieve this message back because it's hashed. It's like in a juice, in a mixer grinder you put various fruits and make the juice out of it. Now you cannot take out your fruits back from the juice. So it's something like that. The fixed length output is used to verify that the original message sent is not changed. So every time if the same message is hashed, it will give you the same output. And that is the use of the hashing to verify the original content, whether it's tampered or not. And we have other uses we'll discuss in following slides. Now symmetric key cryptography. In the example we saw, Julius Caesar is the symmetric key because in this example the keys are same. The same key is used to encrypt the message, same key is used to decrypt the message. That's a symmetric key. So here we have to know the key and it has to be distributed to both the parties. There are few systems like DES, data encryption systems, AES, advanced encryption systems. So AES is mostly used in today's world. Asymmetric cryptography. Here, as the name suggests, the keys are not same. We have 2 keys now. One is public key and one is private key. We give public key to everybody for encryption and private key we keep to us only for opening the message encrypted by the public key. So in this system, any of this key can be used to encrypt and then other key can be used to decrypt the message. RSA is one of the example of the asymmetric key crypto systems. Okay. Hash functions. So hash functions, as we just learned, they are a big message is just converted into a fixed length output. Every time whatever big length message you give, small or big, it will always produce a fixed length output, and that is the hashing. So MD5 for example produces 128-bit output. SHA2 or SHA256 produces 256-bit output. Now how they work? So they take a chunk of your data. So in both of these MD5 and SHA256, they take 512 bits of the data. the actual data that has to be hashed. And they start with some seed bits. So suppose in this example, if you see SHA-256, we start with 256 bits seed value. We take 512 bits of the message block, and we do this algo and produce a 256 bit output. The same 256 bit will then be again used along with the next 512 bits of the message and produce the 256 bits again, and so on. If there are some bits, if we are short of some bits for 512 blocks, we just pad it with zeros, make it a block 512, and continue with this. So at the end we get 256 bits output, and that is our hash with SHA-256. And just to mind you, hash is not reversible. So once you get a hash, you cannot make message out of this hash. So it's one way. Okay, so I've just given two examples here, like a message which says my name is Vipin, and if we do the MD5 hash, we get this output of 128 bits, and if we do SHA-256, then you get this 256 hash out of this message. So what hash exactly do inside? Okay, so they as we said, they do various operations on the bit level. If you see this comparison chart here, MD5 output size is 128 bits. It takes 512 bits of block of the message to be hashed, and then it runs 64 rounds to produce the final output of 128 bits output. Similarly, SHA-256 does the same 64 rounds, takes 512 bits of the data on each iteration, and at the end produces 256 bits output. What does it intermediate in between? It does AND, OR, rotation, modulus, or various kinds of bit level operations, as you can see in the operation section. And this is the pictorial representation of all this bit level operations. So that's how we get a hash. Come back to symmetric key. Symmetric key, as we already seen, we have same key for encryption and same key for decryption. So once you encrypt, the plain text becomes a ciphertext, and you decrypt with the same key, the ciphertext becomes the plain text. The challenge is that both parties should know this key, so it is pre-shared key with both the parties, and they can do encryption and decryption with the same key, calling the similar function. So like for encryption, they call encryption function, provide this key, and the message is encrypted. For decryption, they call decryption function and provide this key, and they get the decrypted or plain text message. Now the challenge again is how we'll distribute these keys, because key distribution, while we are doing it, somebody can copy, somebody can steal this key, and then it can open our messages. So this has to be secured way of key distribution. Another challenge is that if we have 100 friends and you have to send encrypted message to 100 friends, you have to maintain these 100 key pairs at your end, and similarly your friend has to maintain. So there is a lot of key management as well. So this is AES, one example of the symmetric key. This is the mostly used nowadays. This is the mostly used technologies, and so there were DES before, which is data encryption systems, and various others. But then NIST, the National Institute of Standards and Technology USA, they called for a best symmetric key encryption algorithm. They called various people, and then these two Belgian cryptographers, Vincent Raymond and Johan Damon, they submitted this proposal of AES, and it was selected. Why it was selected? Because it used low RAM, and it has high speed, and performance is good on a small computer of 8-bit smart cards and high-end computers as well. So we can get up to 60 megabits per second out throughput on a Pentium which is 1.7 gigahertz. So this is the encryption system we are mostly using in our current cryptography. This chart here does show some rounds how we actually do. So we take blocks of data. If you see each block, there are 16 bytes, and that comes out to be 128 bits. So each block is taken in various rounds. We do various operations. We shift rows, we mix columns, then we put our key, and so on. So I'm not going into much details of the algorithm, but yeah, just to show you how there are complex things inside, but we get it but just by one command, and then our message is encrypted. But why does it take time? So you see what all it does. It takes bits, blocks of your messages and does encryption and puts the output. So sometimes if you see a message, encryption takes time. Here it is the reason. Okay, now how do we key exchange? So one challenge, as we pointed out, exchanging the pre-shared key is a challenge. How we can do it? So Diffie-Hellman devised a way. So if we take two numbers, P modulus and a base G, and both parties know it, we generate our own secret integers. We make our own secret keys. We send it to each other, and then using the other's key, we can make a common key. So how it is does, just in small example, quickly go through it. So P is 23 and G is 5, and this is known to both the parties. Now Alice just chooses some random number, suppose A is equal to 4, and it calculates 5 raised to the power 4 mod 23, so it becomes 4. And similarly B also chooses some random number 3, it does 5 raised to the power 3 mod 23 and makes a number 10. Now B will send this 10 to Alice, and Alice will send this 4 to Bob. Once they receive the other party's this number, they will again do this calculation where suppose Alice has sent 4 to the Bob. Now Bob will, this Bob's private number 10, privately generated number 10, will be done with the power of 4 and will get 18. Similarly, Bob will get the message 4 from the Alice and then its own number 3 and will get the 18. Now both parties have 18 as the common key, and with this they can use any encryption method and send. This is the way. The key never traveled, so nobody knew the key, nobody can steal the key, but still they have the key, common key, which they can use for symmetric key encryptions. Now we come to the asymmetric key encryptions. So as the name suggests, the keys for encryption and keys for decryption, they are two different things. So like Alice first will generate these two keys. So we have various methods like SSH key gen or OpenSSL. You run this command. This command will generate two keys for you. One is private, one is public. The public key you distribute to everybody, and private key you keep it separate to your machine or yourself. And it is all based on the large random number. So public key cryptography is based on the large prime numbers security. So it all depends on the mathematics, that a big prime number identification, and then from a big number you cannot identify what is the factors of these two, factors of that big number. So I'm not going much into the maths, but there's a lot of maths. I will touch base some of the maths in the later slides. So for now, so we have two keys. So one is public, the green one, you send it and distribute to everybody, and red one is your private one. So now Bob, suppose it wants to send to Alice, it will use Alice's public key and encrypt the message. And Alice, once received it, it uses its own private key and gets the message back. Okay. So that way, and how we can further use it for digital signature things, like Alice sends a message, signs with Alice's private key, and sends to the Bob. Bob will use Alice's public key to open that sign and verify that okay, it is Alice indeed. Okay, because the thing is that when you distribute the public key to everyone, anybody can send you any message using your public key. But if you're not sure who has sent it, I mean the person who is saying he is Alice, but he might be somebody else and using your public key. So how you really identify that okay, this is Alice? So that's how this digital signature helps you. So Alice puts some message or sign, you can say, and encrypts it with its own private key. Since only Alice has that private key, only Alice can encrypt it with its private key, and once it reaches Bob, and if that signature opens with the Alice public key, that means it was signed by the Alice private key, and that means it was Alice who has sent this message. So that's how this digital signature works. Cryptographic functions. So what all we can achieve? So we have learned some basics, and now we can see what we can achieve with this cryptographic. So what is authentication? So authentication is you authenticate somebody for who he claims to be. So digital signature is one way, as we just seen. Non-repudiation, means if you order something, you cannot deny because you have signed it. Suppose you send a message to the bank that okay, transfer $5,000 to Bob's account, and later if you want to deny, you cannot, because bank has this message with your signature on it, digital signature, and can claim that you have done it, you have done this transaction, and you cannot deny it. Now integrity of the message. If the message is digitally signed, any change in the message after signature, it invalidates the signature, because sometimes in the signature, what is signature? Basically you can say I am Alice or something, or you can put the hash digest of the whole message, and that message you can do encryption with your own private key. So that serves both the purposes. It will verify that you are Alice, and it will also verify that message you have sent matches, the hash of the message matches with the signature hash. Okay, so that way, if somebody modifies some data, the hash will change, but once you open the signature, that hash will not match with the hash of the new message, and that way you can detect if the integrity is broken. Now the confidentiality, again, if you encrypt the whole message is confidential, and only the recipient can open it. So this is one example, like source A sends something to source B. So what it does, message X first encrypt with own private key, then encrypt with the public key of the B party. B party, when it receives it, opens with the own private key, and then decrypt with the public key of the A party, and that's how the message gets. It serves both the purposes. It will identify that message has been sent by A, and it will also provide the confidentiality. Your whole message is secure. This is also used in HTTPS and certificate case. So if you have seen in your HTTPS sites or secure HTTP sites, you have to use certificates, and that certificates basically have your public key. But the problem is that you claim that okay, I have this is my public key, but you might be somebody else and claiming somebody else public key as yours. So to verify that, we have a system of certificate authorities who will authorize your public key as yours. So some kind of stamping that okay, this is your public key. And these kinds of authorities, they issue your certificate. So what you do, you generate your key pair as we have seen in the last slides, and then you send a request to the certificate signing request to the authorities. So once they sign, that becomes your certificate, and that is now you can say approved, and anybody can use this and trust that it is your certificate. So your site is secure because you provide a certificate, and from the certificate chain or chain of trust, it verifies that okay, you are a real person whom you claim to be. So what is certificate chain? So this, as I said, you go to some CA, but CA is not a single person for whole world. So you have sub CAs, or CA has authorized a few other people to issue certificates on his behalf. So that way we have chain of trust, and each sub CA has to be trusted again. So it has its own certificate, its own public key, which is certified by the primary CA. So this kind of chain, once you log into any secure website or any secure connection, this whole chain has to be verified and tested, and then only you can say that okay, this certificate is valid, this person is valid. This is one example of X.509 certificate. So in this certificate, if you see, there is a serial number, there is a signature algo, then the issuer's identity, and then your validity date, then subjects means it's your identity, and then your key, your public key, and other details. So that way, this is one certificate. You can have multiple keys, multiple certificates within the one certificate. Okay. Now, how you store? So certificates are generally in .pam, .cert, .crt, .dir, .p7b, p12, those kind of formats. We store these certificates, and this web browsers can utilize this certificate from these formats. Encoding formats. Now, as we see, the certificates here is shown in the plain text, but actual certificate is a binary, and it's not stored like this. You cannot open and see this certificate because they are encoded. Okay, so they are stored in TLV format. So we have various encoding techniques like basic encoding rules, BBER, DER, and CER, and we have to store any digital information in some kind of format, because ultimately it's all bits, and we have to take out our message from the bits. So it should follow some structure, some rules of storing and of transmitting. So that way we have various encoding rules. So ASN1 is one mostly used encoding format, and it uses different encoding rules within that. So BER is one of the famous rules, and all these rules basically depend on the type length value. So whatever we want to send, the first will send the type of that message, and then we'll send the total length of that message, and then we'll send the actual message. So this TLV, if we know, then we can always get where message starts, where message ends, where the next type starts, next message end, and so on. So from a big stream of bits 1010, we can always get our message back. Okay, so there are various digital encoding formats, and we'll discuss more about it in the next video.